For over a decade, Docker has been the undisputed king of software deployment. It solved the infamous "it works on my machine" problem by standardizing how we package and ship code. But Docker guarantees that portability through brute force. To make sure your code runs exactly the same way everywhere, Docker forces you to package an entire duplicate file system and a lightweight operating system right alongside it. Take a look at this chart showing the baseline metrics for a standard Docker container. You're looking at 50 to 100 megabytes of memory overhead and a startup latency, the time it takes to actually begin running, of 100 to 500 milliseconds. Carrying the weight of a full operating system for every single application creates a bottleneck. When modern computing demands instantaneous reactions, those milliseconds and megabytes become expensive overhead. In modern cloud infrastructure, tasks like AI agent logic, serverless functions, and edge computing require near-zero reaction times. A half-second delay is often too slow to function at scale. There is a technology built specifically for this ultra-fast, lightweight execution. It's called WebAssembly, or Wasm. But WebAssembly has long faced a major structural limitation. It was architecturally isolated, built to run fast only while trapped inside the secure sandbox of a web browser. Without a way to escape that browser environment, Wasm could not access basic host system resources. It couldn't read local files, allocate outside memory, or open network sockets. To unlock WebAssembly's native speed for server-side infrastructure, developers needed a secure, standardized way for it to communicate with the outside world. That standard is WASI, the WebAssembly System Interface. It acts as an API bridge, allowing WebAssembly modules to communicate directly with any host operating system. Instead of shipping a duplicate OS inside a container, WASI simply asks the existing host operating system to execute the necessary tasks, like reading a file or checking the system clock. Because of this, the structural footprint of a compiled WASI binary is minuscule compared to the heavy, multi-layered environment of a Docker container. By bypassing the need for a bundled operating system layer, developers can strip away the software bloat that traditionally slows down deployment. The WASI component model takes this further by allowing different programming languages to interact natively with each other. Developers can write logic in Rust, another piece in Python, and a third in JavaScript. Those separate pieces then compile and snap together to form a single unified WebAssembly binary. This cross-language compatibility means you can avoid spinning up bulky Docker networks just to get different codebases to talk to each other. Docker secures these applications using ambient authority. If an attacker manages to breach a container, they generally gain broad access to the entire containerized system. WASI counters this with a zero-trust approach called capability-based security. The core rule is a module cannot access files or networks unless the host explicitly grants a handle. If it needs a single directory, it receives access to that directory and nothing else. This strictly defined pathway limits the blast radius of any exploit. Enforcing this zero-trust architecture at the micro-module level makes WASI a highly secure alternative to legacy container deployments. Benchmarks from major cloud providers show the impact of this architectural shift. While Docker functions require a baseline of 100 megabytes of memory, WASI modules operate on 1 to 10 megabytes. And looking at cold start times, the typical 500 millisecond delay in containers drops to 50 microseconds in WASI, a speed increase of 40 times. These performance gains have led platforms like AWS Lambda, Cloudflare, and Fastly to offer dedicated Wasm runtimes to handle their most latency-sensitive workloads. This technology is already operating in the wild, powering serverless functions and routing requests at distributed edge nodes globally. It is even being deployed directly inside major databases like PostgreSQL, allowing developers to run complex computations without risking the main system environment. Docker won't disappear. It remains the standard for large, legacy monolithic applications that require a fully duplicated environment. But for the next generation of scalable, cloud-native software, the overhead of shipping an entire operating system alongside every piece of code is becoming unnecessary.